America is facing a growing water crisis, and one proposed solution sounds almost unbelievable. The idea is simple in concept, but massive in scale. Draw seawater from the Pacific, pump it over mountain ranges, and channel it into Nevada's deserts to form an entirely new inland sea. Supporters say it could help stabilize the Colorado River, store renewable energy, and supply power and water to the Southwest for generations. But behind the bold engineering vision lies a far more troubling possibility. What appears to be a technological lifeline could instead trigger long-term environmental and economic consequences, turning a solution into a slow-moving catastrophe.
Engineering Nevada's ocean ambition. In 2025, the Colorado River Research Group released a devastating report stating that the Colorado River reservoirs are now facing a crisis. This river supplies water to 40 million people across 7 states, 30 tribes, and Mexico, and generates billions of dollars in agricultural output, supplying the U.S. with fruits and vegetables in winter. For the past 2 decades, it has been going dry. Reservoirs that once held 4 years of river flows are now more than 2/3 empty, and if 1 or 2 more years go by without rainfall, their primary storage units, Lake Powell and Lake Mead, would enter a critical threshold. These lakes, especially Lake Mead, serve as the backbone of the water supply for the American Southwest. In fact, reports project that by 2026, Lake Powell will sit at just 48 feet above the minimum power pool, a threshold that, if the lake falls below, the Glen Canyon Dam would no longer generate hydropower for millions, and its ability to release water downstream would be jeopardized. To prevent that scenario, federal and state authorities have put emergency measures in place. Lake Powell will follow planned release schedules that balance water supply needs with hydropower generation downstream. Lake Mead remains in a Level 1 shortage condition, which triggers mandatory water reductions for Arizona, Nevada, and Mexico. Together, these coordinated actions would reduce stress on the system and prevent both reservoirs from dropping to dangerously low levels. But these are short-term fixes. Current guidelines are set to expire at the end of 2026, and officials are urging the 7 Colorado River Basin states to reach a consensus on post-2026 operating rules. Yeah, and this is a big deal for us here in Arizona, because we get about 30% of our water from the Colorado River. Negotiators for the states that tap the river, including us here in Arizona, all in Las Vegas this week, with the water source for some 40 million people hanging in the balance. If the 7 basin states failed to reach a new consensus by 2026, the river would revert to operating rules from the 1960s, which experts call a nightmare scenario incapable of dealing with today's drier reality. However, it is not just the basin facing trouble. Underground, the situation is even more dire. Groundwater aquifers, which communities and farms rely on when river flows drop, are disappearing even faster than surface water in Lakes Powell and Mead.
Despite this, groundwater is poorly managed across the Colorado River Basin and is largely excluded from negotiations over how to share and conserve river water. In Arizona, for example, much of the state has no groundwater regulations, leaving wells running dry and aquifers that would take centuries to recover naturally. Even in areas with some regulation, aquifers continue to decline, and scientists warn that relying increasingly on groundwater to offset river cuts will only worsen losses. Experts stress that surface water and groundwater are interconnected. What happens underground affects rivers and reservoirs and vice versa. Yet, federal and state laws focus almost entirely on surface water, leaving the hidden underground crisis largely unaddressed. Rural Arizona is demanding solutions to protect their water. We will deliver for them, and I'm urging legislators to listen to the voices of rural Arizonans and do the right thing by passing this common-sense legislation. Our futures depend on it. Without coordinated management of both sources, the Southwest risks running out of water entirely. State negotiators may agree on cuts to the Colorado River, but implementing those cuts locally will almost certainly push communities and farmers deeper into groundwater depletion, compounding the crisis and threatening the region's long-term water security. But what if water engineers have found a solution to this? A very ingenious solution that could solve this water crisis once and for all. Researchers have proposed capturing seawater from the Pacific Ocean off the coast of California, desalinating it, and pumping it into arid valleys. In this case, it is Nevada's valleys, the driest of all 7 states affected. But it doesn't stop at supply. The goal is to create one or more giant artificial lakes, an inland sea in places like Panamint Valley, Big Smoke Valley, and Amorosa Valley. The first thing that would puzzle anyone is how does water from the Pacific Ocean get into Nevada? The answer to that is surprisingly straightforward: pipelines. But these aren't just ordinary pipelines. They have to thread across deserts, navigate through mountain ranges, and traverse private and protected lands. Instead of cutting directly through sensitive ecological zones or requiring extensive land expropriation, engineers suggest routing the pipelines along existing transportation corridors, such as Highway 95 and old railway lines. By sticking to these pre-established rights-of-way, the project minimizes conflicts with federal environmental protection laws, land use regulations, and the intricate patchwork of state and private property rights. It also simplifies the installation of pumping stations, maintenance access roads, and the necessary power transmission lines, which can all be integrated into areas with existing infrastructure. From the coast, water would cross the Mojave Desert and reach central Nevada. Even with an optimized route, gravity remains a big issue. The valleys lie between 1,000 and 1,700 meters above sea level, bordered by the Sierra Nevada and the coastal mountains. Lifting water on this scale is physically demanding and energy-hungry. Initial estimates suggest the pumps would require roughly 6 gigawatts of continuous power. To put that into context, the most iconic hydroelectric project in the United States, the Hoover Dam, produces about 2 gigawatts at full capacity. This means that lifting the water would require the equivalent of 3 Hoover Dams running non-stop. Now, if the project relied on fossil fuels like coal, oil, or natural gas to power the massive pumps needed to move billions of gallons of water over mountains and across deserts, it would release huge amounts of carbon dioxide and other greenhouse gases. Even though the plan could help solve the water crisis, relying on fossil fuels would weaken its environmental and climate-friendly claims, potentially turning it into a major source of climate pollution. But what if this same project could also generate its own power and solve the energy problem at the same time?
Making the desert a giant battery. By 2030, Nevada is likely to reach its goal of 50% renewable energy, while California is reported to have 42 gigawatts of installed capacity. These 2 states are leading in solar power generation, and researchers believe this could be the solution to the project's pumping issue. The solution is a system with an underlying mechanism called pumped storage hydroelectricity. When electricity is plentiful and inexpensive, primarily during midday hours when solar output across California and Nevada peaks, the system uses that surplus power to run massive pumps. These pumps perform 2 related tasks. One is logistical, moving desalinated water inland toward Nevada's arid basins. The other is energetic, lifting large volumes of water from the inland sea itself, which acts as a lower reservoir, into a second reservoir positioned at a significantly higher elevation. In doing so, electrical energy is converted into gravitational potential energy, stored not in batteries or chemical bonds, but in water held in reserve above the desert floor. The energy generated by the system appears only when this process is reversed. As solar production collapses in the evening and electricity demand rises, water is released from the upper reservoir and directed downhill through pressurized pipes. Turbines embedded along this descent convert the kinetic energy of falling water into electricity, feeding power back into the grid during hours when prices are highest and supply is most constrained. The electricity produced is hydroelectric, dispatchable on demand, and carbon-free at the point of generation. But because of mechanical losses in pumping, friction in pipelines, and turbine inefficiencies, the system returns less energy than it consumes, typically on the order of 70 to 80% of the original input. The remaining energy is lost as heat, an unavoidable feature of storage at this scale. There is also a financial logic embedded in this design. Electricity prices tend to collapse during periods of excess solar generation and spike after sunset. By consuming power when it is cheapest and selling it back when it is most valuable, the project attempts to offset part of its own operating costs. However, the engineering assumptions underlying this model leave several critical challenges unresolved. The scale of energy losses becomes significant when multiplied across gigawatts of continuous operation.
This translates into vast amounts of electricity wasted daily. Unlike traditional pumped storage facilities, which cycle the same water repeatedly between two reservoirs, this system must also permanently move water inland, creating a constant energy draw that persists even as market prices rise. Also, the physical infrastructure required to support this operation causes additional strain. Solar overproduction occurs in specific geographic zones, while pumping stations, reservoirs, and demand centers are distributed across long distances. Transmitting large amounts of power between these points requires extensive grid upgrades, new transmission corridors, and regulatory approvals that are often slower and more expensive. Environmental and geological uncertainties also accumulate over time. Repeatedly cycling massive water volumes through newly constructed reservoirs increases risks of seepage, evaporation, land subsidence, and induced seismicity. In arid climates, evaporative losses alone can erode storage efficiency, especially over multi-decade timeframes. These effects are not easily modeled at full scale and tend to emerge gradually rather than immediately. There is also exposure to market risk. The economic viability of the system depends on persistent price spreads between daytime and nighttime electricity, continued dominance of solar generation, and limited competition from alternative storage technologies. Advances in battery storage, thermal systems, or hydrogen could compress those spreads, reducing the financial advantage of pumped hydro at an extreme scale. Finally, the system tightly couples two critical resources: water delivery and energy storage. During periods of energy scarcity or price volatility, operational priorities may conflict. Decisions about whether to release water for power generation or retain it for long-term water security introduce political and operational pressures that conventional power plants do not face. The engineering design assumes these trade-offs can be managed, but it does not eliminate them. But even if the project is successful, how do people consume the salty seawater? The desalination dilemma. The transformation of Pacific seawater into a usable inland resource is possible through large-scale reverse osmosis desalination. Seawater is pressurized to roughly 1,000 pounds per square inch and forced through semi-permeable membranes whose pore size allows water molecules to pass, while rejecting dissolved salts, minerals, microorganisms, and most organic compounds. The output is split into two streams, one of low-salinity freshwater suitable for municipal and agricultural use, and another of concentrated brine, typically about twice as saline as the source ocean water. Facilities such as the Claude Bud Lewis Carlsbad Desalination Plant in San Diego demonstrate that this chemistry works reliably at scale, producing approximately 50 million gallons of fresh water per day through continuous membrane operation. That same facility, however, also illustrates the magnitude problem embedded in the inland sea proposal. Carlsbad is among the largest desalination plants in the United States and supplies roughly 10% of the San Diego region's water demand. The inland sea concept requires an entirely different order of magnitude.
Creating and sustaining a large artificial inland body of water while also supplementing regional water supplies would demand desalination capacity not incrementally larger but exponentially larger. Estimates suggest that offsetting even 10% of the Colorado River's current flow would require desalination capacity on the order of 14 times that of Carlsbad. At that scale, the system ceases to be a single plant and becomes a vast industrial complex composed of thousands of membrane modules, redundant pumping systems, and continuous chemical pre-treatment operations. Pre-treatment is one of the most demanding components of the system. Raw seawater contains suspended sediments, organic matter, microorganisms, and seasonal algal blooms that can rapidly foul reverse osmosis membranes. To prevent this, incoming water must be filtered, chemically conditioned, and disinfected before it ever reaches the membranes. At the inland sea scale, this pre-treatment infrastructure resembles a full chemical processing facility, requiring constant dosing of coagulants, biocides, and antiscalants, as well as continuous monitoring and replacement of membrane elements. Each additional layer of treatment adds cost, complexity, and operational risk, particularly when multiplied across dozens of parallel desalination trains operating without interruption. Alongside fresh water production, the process generates an equally large volume of concentrated brine. For every gallon of potable water produced, roughly 1 gallon of brine remains.
At the scale envisioned, this waste stream becomes a central environmental constraint rather than a peripheral issue. Discharging dense brine back into coastal waters can cause it to sink and spread along the seafloor, increasing salinity to levels that stress or kill benthic organisms. Residual treatment chemicals and trace metals from pipe and pump corrosion can further compound these effects. Managing brine responsibly at this volume would likely require extensive dilution systems, offshore diffusers, or additional treatment processes, all of which increase energy use and infrastructure demands. Rather than treating this brine solely as waste, some proponents point to its latent mineral value, particularly lithium, as a potential offset to both environmental and economic costs. Lithium occurs in seawater at trace concentrations and becomes more concentrated as water is removed through desalination and evaporation. In theory, a system processing ocean-scale volumes of water could accumulate brine streams rich enough to justify mineral recovery, especially as demand for battery materials accelerates. This makes the project even more promising and shows that the inland sea could evolve into a strategic resource hub, producing not only water and energy storage, but also critical materials for the energy transition. However, the practical constraints are severe. Ocean-derived brine contains lithium at concentrations orders of magnitude lower than those in natural salt flats, requiring advanced separation technologies, such as ion-selective membranes or solvent-based systems. These processes are energy-intensive, sensitive to fluctuations in brine chemistry, and largely unproven at the sustained throughputs implied by the project. More importantly, mineral extraction does not eliminate the brine, it transforms it. Lithium recovery leaves behind even more chemically complex residual streams enriched in other salts and processing reagents, which must still be managed within a closed or semi-closed system. In a terminal basin or coastal discharge environment, these residues remain part of the same accumulation problem they were meant to solve.